Hey guys, another final GPIO Microtronic Next Generation test. Thanks to my previous video, my project partner Frank from Belgium, who's the developer of the electronics Microtronic second generation sister project of the Next Generation, pointed out that my 2075 counter module was behaving oddly. And the reason for this is I checked my source code and I actually measured the outputs of the next generation board with my voltmeter, and I saw that I had inadvertently inverted the outputs. So the digital 0 came as 5 volts and vice versa. So I had some active low actually, whereas they really need to be active high. So in the official Microtronic, both the inputs and the outputs are active high, and this is what you need in order to run the experiments. So then with the firmware fixed and the output level is now really positive TTL as it should be with active high, I then figured it might be a good idea to run an official test program from the manual. This is a second Microtronic manual. And there is an experiment here, an official program that involves the 2075 counter module, similar to what I showed you in the last video. The experiment is on page 59 and it's called Principles of Data Transmission. So data transmission with only 3 lines, and the setup is shown with the original Microtronic and original counter module on the next side. So we have 2 outputs here, and one output is connected to the clock signal of the 2075 counter and the other one provides the reset. And as we will see, the reset is actually low active in the 2075, and also the clock signal requires a falling edge, so a high-low transition. So what that program does is, so I've already stored it and keyed it in, so I only need to start and run it here, is you can enter a number on the keypad, right? And that number then toggles the clock signal, and the counter module is first reset, and then it counts up to the number you entered over the keypad. So I'm not going to step through the program how it does that, but rather we just run it. So I can now enter, for example, 1, and you see that the counter got one clock signal pulse, and it also counted to 1. And if we count to 6, then it counts to 6, and so on. And so that works well now, and that's the way it ought to work. And you can see that now these are the 2 outputs here, the bit 1 and bit 2, or I should say 0 and 1, right, which are clock and reset lines, that they are both high, right? So this module is really low active. You see if I toggle it now, right, I sent a 9 here, that it makes high-low transition for the counter to work. And also the reset pin is low active, so those things are held high, and only when the counting is happening they are triggered low, right? So then Frank also designed a new 4029 counter module, and he asked me if this experiment would also work with his new counter module. Unlike the old 2075 counter, he does not have a 7-segment LED display here, but he has binary output. And what you see is counting works well with the clock signal, right? So it correctly reacts to the high-low transitions, and it shows the same value as the official counter. That's an 8, that's a 1, that's a 2, that's a 4. 7 should show all 3 LEDs set, right? However, his reset line is high active, right? And that's the difference to this counter, where the reset line is low active. You can see it here, right? I mean, it's actually high now, so this is why it's keeping its value and is not being reset. Whereas for Frank's module, I now needed to use an inverter gate, the Bush inverter module, in order to invert the reset signal, right? So then it correctly counts, then it correctly resets, right? So if I just pull, of course, the reset line, then it would no longer reset, right? So it would just keep counting up, right? But would not count to the right number. So that's the output of the inverter, and I can also show you if I put the same signal in here that the 2075 counter gets, right? The inverted reset signal, then you will see that it's actually constantly held in reset now, because its reset is high active, whereas this is low active, and you see that it's not counting at all, right? So I really need to invert the signal for it to work. So let me put that back. Just a simple inverter. And then you will see it's going to count again. So yeah, but overall that's still a very good and useful module, even though you need to invert the reset signal. Alright guys, thanks for watching.